Good afternoon, everyone. My name is Aggarwal, and I'm currently working as a research associate at Dynamic Decision Making Lab, SDS Department at Carnegie Mellon University. Today, I'm pleased to present our paper titled Cognitive Biases in the Cyber Attacker Decision Making, Translating the Behavioral Insights into Cybersecurity. This work was conducted in collaboration with Maria Jose Ferrara, Palvi Aggarwal, Prashant Rajivan, and Cleotilde Gonzalez, who's my supervisor. I would really like to thank my collaborators for their constant guidance and hard work in this research. Additionally, I would like to extend my thank you to the Paraton Labs for their work in the cyber-related scenarios, and Jeffrey Flagg, who is our lab manager at DTM Lab, for making this experiment success. I would also like to bring into notice that this research was funded by IARPA under the Recency program. Special thanks to the workshop organizer for this opportunity to share our work, for allowing me to present remotely. I regret that I'm unable to attend it in person, but I truly appreciate the chance to participate on this virtually. Thank you. So, behind every attack, there is a human mind, and humans tend to make errors which can be caused by different human behaviors like overconfidence, lack of patience, or the risk seeking or the risk averse behaviors. If we understand our enemy better, there's a chance that there's a possibility that we can defend better, right? So, to do so, we need to figure out how these errors or the cognitive biases can be identified in the attacker. There's a vast literature of the cognitive biases by Tversky and Kahneman's work in availability bias or the loss aversion, etc. But when we look into the cyber domain, this exploration is very, very limited when it comes to studying the cognitive biases in attackers. Mostly the existing works focus on the identifying the biases by analyzing the patterns in existing data sets, which were not originally designed for the cognitive biases measurements, or the manipulations are being done in the simulated environments. There is a major gap which needs to be understood, and there is a major gap to understand and use the formal methods of the bias measurements from our established literature. Our focus of this study is going to leverage these existing definitions and replicate them in the cyber domain. We are calling this concept as the cyber isomorphs or the cyber methods. So the main research problem statements that we are addressing for this paper are whether we can replicate the cognitive biases in cyber domain, or are there any additional human individual differences that can have an impact on the cognitive biases present in the humans. So we ran the study as a within subject design. We recruited 148 participants from the prolific, and out of those, they were screened based on a theoretical cyber knowledge and were judged based on if they are doing the minimum of 7 questions correct out of 9 questions. We got total 92 who passed the screening test. These 92 participants were given the 12 questions with the binary outcomes. 6 of them were the established methods, which are called EMs, and then 6 were from the cyber methods, which we are calling the CMs. These 6 cyber methods were, these 6 each condition methods were covering the 6 cognitive biases, which are availability measured as the frequency and recall, and then there is a recency, and then loss aversion measured as the endowment, gain, and loss frames. In addition to these, we also collected some psychometric questions like GRIPS, cognitive reflection test, CRT, intuitiveness and reflectiveness, or the ADMC, resistance to framing effects, and sunk cost. We also collected the practical cyber knowledge to understand how knowledgeable how much experience or how knowledgeable they are in the cyber domain. So our cyber isomorph design is based on like choosing one example or experiment from these established literature and then creating the replica of those established methods into the cyber domain, which we are referring as cyber methods. So let's try to understand this process of cyber isomorph creations. I'm taking an example of the availability recall. So availability bias is the tendency to prioritize or remember the information which is readily available in mind. And from the literature, we took example from the Tversky and Kahneman's work in 1973. where they presented the participants with the two list of the names which had famous and less famous. As you can see in the videos being played on the screen, we also presented the participants with these lists of the names, with each name being displayed for exactly 2 seconds. These lists were given one after the other. So in this design, when the two lists are considered overall, the number of famous and less famous were same. The participants were then asked to recall, after they witnessed these videos, they were asked to recall how many famous and less famous names they can recall. So our hypothesis in this is the participants will be recalling more of the famous as compared to the less famous, and this will be the indication of the existence of availability recall bias. So when we try to replicate this in the cyber domain, our main question was what would be the alternative of the famous in the cybersecurity domain. So we all are aware that selection of the vulnerability by the attacker is a crucial step for them. It involves the decision making. Let's say an attacker find multiple vulnerabilities on the machine. They need to make some decision on to choose which vulnerability are they going to exploit. These decisions can be based on their familiarity with the vulnerabilities, or they might look into the CVSS score, seeing how critical this vulnerability is. So we chose the CVSS score as the criticality, which is defining the criticality of the vulnerabilities as the famous and the less famous. So the CVSS score greater than equal to 9 are the critical and less than 9 are the less critical ones. So we presented the participant with the two list of the vulnerabilities which contain the CVE number, vulnerability names, and the CVSS score. We later asked them to recall the names of the vulnerabilities they can remember. Each of these, when these lists are considered together, there was an equal amount of the critical and the less critical or the rare vulnerabilities. However, the hypothesis that we are having here is participants are going to recall more of the critical over the less critical vulnerabilities, even though the frequencies are same. So we found it interesting to we tried to strategically leverage this prioritization of critical over the less critical vulnerabilities in this particular scenario. So if I take one more example from the recency bias, so recency bias is overemphasizing over the recent events. For this, from the literature, we chose the work of Neetu et al. 2021, where they created a personalized travel recommendation system. In this, one of the step involved using the recency bias for recommending the travels. They analyzed the tweet wall of the participants and then how the recent tweets by their friends are going to influence their travel choices. How they influence their travel interest for the participants. To replicate this, we presented the participants with the 6 tweets, with each tweet showing the date and the number of likes. The date represented the recency of that, and the number of likes represents the popularity of the tweets. So for the biased participants, for the recently widespread event, they might ignore all the other information such as the popularity of the tweets and just focus on more recent activities as compared to the older ones. For the cyber isomorph or for the cyber domain, we considered using the output of the history command. So let's say so the history command is where it shows the history of the commands used by the logged in user in a chronological order. So let's say the attacker is trying to identify the important information present in the machine, what are the files or the folders they can visit. There is a possibility that within a limited time frame, if a machine has a lots of data, it's hard for the attacker to identify where to go and where to look into. So they might go and look into the history command output, and based on what this user's recent activity is, they might make the decision on which directories or the files to visit. So the attacker who is biased with the recency is going to prefer the latest command as highlighted in the image as compared to the older commands. So yeah, this is the process of how we created these cyber isomorphs. I'm showing all the isomorphs that we created, the cyber methods, in the tabular form for each of these biases. And for some of the biases, we had more than one variation or the context. For example, for the availability frequency, we had the operating system scans, we had the alternate port scans, or the vulnerability scans. However, each participant was assigned just one of these variations randomly chosen for each of the bias. Yes, there was a variation in how the each of these contexts performed by the participants, but for this paper, we are focusing more on the global level rather than going into the individual variation level results. So this is the table that shows all the variations that we used, all the manipulation for each of these biases. I'm not going into too much detail of this, but we can discuss towards the end if anyone is interested. So So now coming back to the problem statement that I highlighted in the beginning. First statement is, can we replicate the cognitive biases in cyber domain? So this graph is showing the answer to the question that we raised earlier. If we look into the plot, the x-axis represent the 6 cognitive biases, which are differentiated by the colors of the parent bias, like peach for the availability, and green for the loss aversion, and blue for the recency. Now, the y-axis shows the average proportion of these biases on an aggregate level. The dark bars are for the established methods and the lighter bars are for the cyber methods. If we look into the availability, we have the two contexts, the frequency and the recall. Looking at the frequency, we observed that 46% of the participants were biased in established method and 51% were biased in cyber method. We ran the McNamara test to understand and see how statistically significant the differences between the established method and cyber method are. And that's the differences were not statistically significant for the availability frequency, which shows that this replication was successful from EM to CM. However, when we look into the recall, we observe that 84% were biased in the established method, while 52% were biased in the cyber method. These differences were observed to be statistically significant, as marked as a star in the bars, reflecting that these were not replicated successfully. So if we look into the other biases, the endowment, the loss frame, and recency were replicated, while the gain frame was again not replicated in the cyber domain. So, what could be the possible reasons for these availability, recall, and the gain frame to not being replicated? We were more interested into understanding these failures in this replication. So, if we dig deeper in these two biases and we look into the how the variation was between the EM and the CM, we looked into the consistencies and the inconsistencies, and we define these 4 categories. We are saying positive consistent if they are biased in both EM and CM, negatively consistent if they are unbiased in both EM and CM, and EM inconsistency if they are biased in EM and unbiased in CM, and CM inconsistency if they are unbiased in EM and biased in CM. So yeah, so if we look into the plots to better understand how they are varying between the consistent and inconsistent behaviors, we observed that most of the people were consistently biased in both established method and cyber method rather than being not biased, which is a good thing, right? So we have this positive showing the higher percentage of the participants. And when we looked at the inconsistencies, people were more biased in the established method as compared to the cyber method. So this raises a question on whether these cyber isomorphs of the methods were generated correctly for the recall and the gain frame, or there are some additional individual human factors which might have an influence on participants' decisions for these two particular biases. To understand this is our second problem statement. And to understand this, we ran the Pearson correlation analysis. The results show that the participants who are more knowledgeable in cyber are less sensitive to recall in established method. And they are more consistent in their lack of bias in both established and cyber methods. And if we look into the grip score, People who are more risk seeking, they tend to choose the risky choices in game frame, which makes sense, right? And the risk seeking are also less sensitive to the recall bias in established method. Additionally, they were also more consistent in the lack of bias in both established and cyber method conditions. Um, Additionally, when we looked into the CRT intuitiveness and reflectiveness score, people who are more thoughtful tend to choose the safer option in the game frame in cyber domain, and who are more intuitive, they tend to choose the risky option of the game frames in the cyber domain. Additionally, the intuitive people were also more inconsistent in their responses between established and the cyber methods. They're more biased in established as compared to the cyber conditions. So, to summarize all these key takeaways and to summarize all these results, we observed that there was a successful replication for the frequency, recency, endowment, and loss rate. And there was a failure in replication for the availability, recall, and gain frame because of the inconsistencies observed. These inconsistencies are explained by the individual differences. So, having a good practical knowledge makes the participants less biased in both EM and CM conditions. And the risk seeking behavior makes people less biased in both EM and CM conditions. Additionally, the participants engage in more deliberate reasoning when they are faced with the cybersecurity problems as compared to while they are relying on more on the intuition if looked into the established method scenarios. So some of the limitations that we observed in this are we didn't include the control scenarios for these cyber isomorph triggers. It would have been nice if we had the controls and looking into the comparison of the control and the trigger conditions on how the participants are performing. So this is our limitation which we are planning to handle, which we are planning to tackle in the future. So we also had a smaller sample size for these correlations. And another thing is there is a this is more of a theoretical assessment of these isomorphs, and they really need to be evaluated in the real world scenarios because it can be challenging if we try to implement them as it is in the real world. This brings me to the next slide of mine where I talk about the challenges towards the realism and the future work. So if we consider the recall scenario, we presented the participant with the vulnerability names and the CVSS score. Now, these two can confound the participant responses, blurring the impact of the cognitive biases and the informed reasoning. So, one possibility is we only present them with the CVSS score, or we present them with both, but then the context of how they are going to, or the goal towards which they need to achieve it, might have an influence on what the participant is choosing, whether they are relying on the CVSS score or the vulnerability names. And what does impact their decision making. So these sort of changes can be made in the isomorph for the future studies. And when we look into the gain frame, I believe that the context influence the risk prioritization, and that might be driven by the order in which the decisions are being made. So, for example, if we take the example of a cyber kill chain phases, so let's say if the participant is or the attacker is in the early stage of the kill chain, they might go with the safer choice because they don't want to take the risk since they're still trying to get into the network. But once they are in the network, they have explored the things and they are very close to achieving their goal or their towards the end of the kill chain. There is a possibility they might take a little bit of risk as compared to play safe. And that influence their decisions, and the context is what is defining how they're going to behave in the same game frame scenario. They can be risk averse in the beginning, but they can be risk seeking towards the end. So testing these kind of things when it comes to the constant decision making in the attack flows is what our future work is going to cover. Similarly, if we talk about the endowment effect, it is challenging in the digital scenarios to kind of develop the sense of ownership of the scenarios, right? So these sort of decisions can be tested, need to be tested in the in a more realistic settings where which we are planning for our future work, where we will be mapping the cyber attack flows and then guide the decision making in the cyber kill chain, and then assess these biases as we move towards the end. Yeah, thank you.